Hi everyone, this is a test of the live streaming feature of OBS Studio. I'm currently at home in Melbourne. I just want to see whether this works. So this video is really an introduction to Pythagoras Theorem, and my target audience is Year 10 maths. So you've seen Pythagoras' theorem in Year 9, and we want to be really fluid and confident with it this year in Year 10. So let us begin. We're going to start with angles. So if I stand on the ground and turn around, then if I turn around in such a way that I end up facing the way that I started and undertake a full rotation, I'm going to define that as 360 degrees. Degree is just a unit of rotation. So if I do a full rotation, and that's 360 degrees, if I only do half a rotation, which would mean I'm facing backwards from where I started, that would be half of 360 degrees, giving me 180 degrees. Now, we can go further. So if I only did a quarter rotation, this would be like facing the front and then facing to the right. Or to the left, it doesn't matter. If I divide 360 by 4, I get 90. And the number 90 is special because it makes our calculations a lot easier, as you will see in a moment. And we give this a name. So a right angle refers to 90 degrees. And all the mathematics that we're going to be doing in this topic, beginning with Pythagoras' theorem in this video and trigonometry in a future video, we'll start by looking at right-angled triangles. Of course, not every triangle in the world is right-angled, but in our journey of learning techniques to deal with triangles, the simplest case is the right-angled triangle. So we're going to spend most of our time to begin with in cases where we have a 90-degree angle somewhere. Wherever you see this little square, that means the angle is 90, and that's a well-recognized symbol all around the world that every mathematician will recognize. So for example, say I draw this triangle and I draw a square. That means the angle is 90 degrees. There. Okay, so right-angled triangles. For now, we're just going to say that a triangle has 3 sides, and those sides are straight. And I want to teach you a word. That word is hypotenuse. Sounds very long and technical, but it's very simple. It just means the longest side. Now, we'll probably do an activity in class, but the claim that I want to make now, which you may or may not believe, is that if I want to find the longest side in a right-angled triangle, the first thing I should do is find the right angle. There it is. And then look for the side that is opposite that angle. So in this case, this is the side that I'm talking about here. That's the hypotenuse. In other words, the biggest side is going to be opposite the biggest angle. In a triangle, the angles add up to 180. And in a right-angled triangle, I claim, I'll leave this to you as an exercise, the biggest angle is 90 degrees. So if you're happy to believe me when I say the biggest side will be opposite the biggest angle, and the biggest angle is always going to be 90 degrees, then all I have to do is find the right angle, look opposite, and there's my hypotenuse. If you forget what hypotenuse means, just remember it means the longest side. Okay, now that I've given you a definition for the hypotenuse and the definition for a right angle, we're now ready to state Pythagoras' theorem. So here it is. In any right-angled triangle, doesn't matter how long the sides are, as long as it's a triangle, as long as it's right-angled, then I get this really, really nice, simple formula. A squared plus b squared equals c squared. Now, if you have forgotten, just remember a squared means a times a, b squared means b times b, and c squared means c times c. In other words, if I square a number or raise it to the power of 2, that's the same as taking that number and multiplying it by itself. So one way to think about this is, here's my triangle. If I make a square out of the smaller side lengths, then what should happen is if I add the two smaller squares, I should get the area of the bigger square. So those two black squares, if I take their areas and add them together, I should get once I've combined them, I should get the area of the bigger orange square. Now, that's the claim. I haven't convinced you why this is true. I will talk about this in class. Feel free to just search it online. There's a few simple proofs that involve some Year 9 algebra or finding the area of squares and triangles. But for now, here's the formula. A squared plus b squared equals c squared. And for most of this unit, our focus will be on using it to find unknown side lengths in right-angled triangles. So let's do a few examples. So I want to start by finding a longer side. Remember, the longer side is the hypotenuse. So I think I'll just say solving for the hypotenuse here. So remember, hypotenuse is opposite the right angle. And I've labeled the side lengths 5, 12, and x, the unknown, for the hypotenuse. How on earth do we find x? Well, if we didn't know Pythagoras' theorem, what we would have to do is draw a triangle with side lengths of 5 and 12 at right angles, and then use a ruler to measure the remaining side length. But we have a result. We have a formula. So I'm going to start by labeling the sides. A, B, and C. And Pythagoras' theorem told us that a squared plus b squared equals c squared. So that means if I replace a with 5, b with 12, and c with x, I can write 5 squared plus 12 squared equals x squared. And now what I want you to notice is that I've got an equation that I can now solve for x. So let's go ahead and do that. Let's simplify 5 squared and 12 squared. And let's simplify the equation and we'll get a number, a length for x. So let's start with 5 squared. 5 squared just means 5 times 5. And that gives us 25. 12 squared, that's 12 times 12, 144. That gives me x squared. So I can take 25 and 144 and add them together. So let's do that. 169 equals x squared. And now it might not be entirely clear what we need to do because I can't use plus, minus, times, or divide here. What I want to do is go from x squared to x. So I'm just going to give it to you. If I want to reverse the square, then what I should do is do what's called the square root. So, in other words, to go from this line to this line, what I'm doing is taking the square root of both sides. And we are assuming that x is a positive number. When I measure this side length, x, I don't want to use a negative number. So those of you who've studied quadratic equations, you'll know that really I should have plus or minus here. But because I've made this assumption that x is positive, I can just assume that I'm going to have a positive number at the end. Now, at this point, usually you'll need to use a calculator. It just so happens in this specific case, we actually get a whole number. Most of the time you won't. I've just made this example simple so that it's straightforward. If not, you'll need to go to a calculator and find the square root button. So this is actually a CAS calculator, but you're looking for this symbol. I'll type in the number 169 and it's going to give us 13. It's a well-known number. So if I had one more line of room, I would write x equals 13. And that's my final answer. Okay, so we're done. So let me summarize the steps. The first thing I did was I wrote down Pythagoras' theorem, a squared plus b squared equals c squared. When you've got a lot of experience, you won't need to do this anymore and you won't need to label a, b, and c explicitly on the triangle. But if you're feeling rusty or it's been a very long time since you've done this, then go ahead and do that. It's going to make it easier. Then replace a, b, and c with the numbers in the triangle. 5 and 12, and x for the letter. Square your numbers, and then take the square roots to go from x squared to x. And that's it. You can follow this exact same process when there are decimals involved as well. Alright, let's do another example. This time, we want to solve for one of the shorter sides in the triangle. Now, notice I didn't label the right angle. That's very bad. We need to assume that this is a right angle to use Pythagoras' theorem. Notice that the hypotenuse was given this time. It's 25. So this time, I'm not going to be solving for the longest side. I'm solving for one of the other two shorter sides. And here I've called that side x. So let's start by labeling the sides of the triangle A, B, and C and write down Pythagoras' theorem. A squared plus B squared equals C squared. We can replace the numbers. So 24 squared plus x squared equals 25 squared. Now, you might know your times tables up to 12 times 12. You probably don't know 24 times 24, although you might have strategies to work it out. You're welcome to just use a calculator. If you've done a lot of these calculations, you'll end up memorizing the numbers. So 576 plus x squared equals 625. You should notice that this equation looks quite different. Here, the x squared is being added to a number. In this case, the number is 576. Whereas before, the x squared was on its own. And that's because in Pythagoras' theorem, the hypotenuse is on its own. So I'm expecting that if I'm not solving for the hypotenuse, if I'm solving for one of the shorter sides, the x is going to appear grouped with one of the other side lengths squared. So remember, our goal is to find x. So when I'm finished, I need to be able to write down x equals some number. Right now I can't. I've got this 576 with the x. So let's get rid of that. Now, I've added 576. So what I should do is subtract 76 from both sides. This is the sort of working out you did in algebra when solving linear equations. You're welcome to do that here. If you're feeling confident, you don't need to write that. So if I take 576 minus 576 on the left, I'll be left with 0. On the right, if I do 625 minus 576, I'll be left with 49. And notice, now that I've taken away 576, I've got an equation x squared equals some number. So I'm really close. I want to be able to write down x equals some number. So, what was the step? To go from x squared to x, I had to do something to both sides of the equation. And that step was to take the square root of both sides. So if I do something to one side of the equation, I've got to do it to the other side as well. So here I need to take the square root of 49. And in this case, you can use a calculator or your times tables knowledge. There is a number which, if I multiply that number by itself, I do get 49, and that number is 7. And we are done. So let's summarize. Our first step was the same. We wrote down Pythagoras' theorem. A squared plus b squared equals c squared. Then I substituted the numbers that I knew. So in this case, I replaced a and c with 24 and 25. I squared the numbers. And this time, I had to do a little bit more work. I had to take away 576 from both sides before I could take the square root. To go from x squared to x. As you're getting used to doing these calculations, you'll want to be sure whether you are solving for the hypotenuse, which we did first, and here the calculation is simpler. So you want to be sure whether you're solving for the hypotenuse or you are solving for one of the shorter sides instead. Because if you're doing the shorter side, the calculation takes a little bit longer, but it's still reasonably straightforward once you've got some practice in. Okay, I want to finish with one more example, and that is a calculation in 3 dimensions. Believe it or not, we can use Pythagoras' theorem here as well. And you might be saying to me, Mr. Chu, I understand that you want to find the length from this point A to this point G, but that's in 3 dimensions. And Pythagoras' theorem applies for right-angled triangles, and those are in 2 dimensions. How can I apply a 2-dimensional technique in 3 dimensions? Well, I'm glad you asked. The key here is to recognize that there are actually right-angled triangles that we can use to get to AG. So what I'm going to do is I'm going to start with the triangle on the bottom, A, B, C. So I colored it in green, so I'll color that line green. And then there's another right-angled triangle, ACG. So here's AC in green, and then AG, which is the length that I'm looking for, in red. Do you see that? They're both right-angled triangles. So if I can find AC, then I can combine that with CG in the second right-angled triangle to find AG. Okay. Let's label the information that we know. So first, AB. Do we know AB? Yes. AB is 10. Do we know BC? At first, it might not look like it because I haven't written down BC here. But I have told you that this is a rectangular prism, which means parallel sides have the same length. In this case, BC is parallel to AD, which means BC is 5. Finally, CG. Do we know CG? It's not labeled here, but again, CG is parallel to AE, which means CG equals 3. So, if I can figure out this green line using Pythagoras' theorem, then I can do another calculation using the green line and 3 to find the red line. Alright, so how would we write this out? I'm going to use some notation that you might not have seen before. I'm going to use AB to mean the length of the straight line joining A to B. For instance, in the first triangle, I can say AB squared plus BC squared equals AC squared. And then in the second triangle, I can say AC squared plus CG squared equals AG squared. So remember, my goal is to find AG. In order to find AG, I have a sub-goal where I need to find AC. And actually, I don't really need AC, I just need AC squared. So I'm going to show my working out reflecting that. I'm just going to work out AC squared. So let's substitute the numbers. AB is 10, so 10 squared plus 5 squared equals AC squared. 10 times 10 is 100. 5 times 5 is 25. So therefore, AC squared equals 125. And I'm not going to bother square rooting because my formula for AG involves AC squared. So now I can just put in 125 here. And CG is 3 squared. So 125 plus 9 is 134. Which means AG equals the square root of 134. Remember, to go from a number squared back to the original number, the operation that I need to do is called the square root. 134 is not one of those numbers that gives me a nice whole number when I take the square root, so we will need to use a calculator here. If you are using a CAS calculator, you can find the correct button, or you can actually just type in the abbreviation SQRT for square roots. So the number that we wanted was 134. And you'll notice on the CAS, if you haven't changed your settings, it's just going to give you the same number back. That's not what we want. This is called an exact value. If I want a decimal approximation to an exact value, then I need to press Control Enter. So Control is that blue button, so press Control Enter. And there you go. There's our approximation. So with the magic of technology, I'll just move this all up one line. So AG equals 11.5758.369. And this number actually goes on forever. This is called an irrational number. The decimal digits go on forever and there's no pattern. What we usually do here is we have to approximate this number. So we'll round. If you're doing a test, you'll be told how much to round. A good rule of thumb, if you're not told, is to round to 2 decimal places. So I'm going to say AG is approximately equal to 11.58. And the reason why I've rounded up is because this third digit after the second decimal place is 5 or larger. So if the number is 5, 6, 7, 8, or 9, I round up. Otherwise, I'll round down, but here I round up because the number is 5. Okay, that is a very, very quick introduction to Pythagoras' theorem. See you in the next video.